fine.
All right, so probably begin. Okay, so we have here today Dr. Garima Singh from Gemini Observatory. Prabal and I met Garima last year at an Indian exoplanet conference, and we were really impressed with the way she described the coronagraphy techniques and the basics of coronagraphy. That's one of the best talks I've heard because it was not technical. She went through all basics of direct imaging techniques. Garima did a PhD with Olivier Guillot, Subaru, and I thought it would be an interesting talk and concept for her to come over here and meet people. So Garima, whenever you're ready, please go ahead.
Okay. Well, good morning. Thank you, Ravi, for the introduction. I am an adaptive optics scientist, as well as a project scientist for Gemini Planet Imager 2 instrument at Gemini North Observatory, which is on the Big Island of Hawaii. Before I proceed, I would like to do the land acknowledgement. He ali'i ka aina, he ka ua ke kanaka. It's a Hawaiian proverb that emphasizes the interconnectedness between the land and the people of the place. We as scientists and educators acknowledge this interconnectedness between Kanaka and their land. We recognize that we have a kuleana that comes with the opportunity to pursue astronomical research on Mauna Kea, and that it is our kuleana to build and continue to strengthen healthy relationship with the land and the people of this amazing place. So I'm going to talk to you today about Gemini Planet Imager instrument. It's a high contrast imaging instrument which takes direct images of exoplanets. So the work on GPI that I'll be presenting here is on behalf of all of these wonderful people who have developed this instrument and also made it an on-sky success. My involvement in the project will be more active in a couple of months we're going to go into the pre-commissioning phase of the instrument. So I'll be working more proactively on the project. So in this talk, I'm going to dedicate half of my time in explaining how do we do direct imaging with the ground-based telescopes. And then I'm going to introduce Gemini Planet Imager 1. It operated for 6 years. It was at Gemini South in Chile. And it operated for 6 years, and now it's off the telescope, and it's now going under upgrade in the mainland US. So GPI 2 is supposed to come at Gemini North probably by the end of the year, and we're going to be commissioning this instrument early next year. And if we have time, then I'm going to explain some of the challenges that GPI 2 instrument will face at Gemini North. So in this talk, I will refer to 3 different instruments. One is, of course, GPI at Gemini. The other one is Skexeo instrument, which is also a high contrast imaging instrument at Subaru, that's also on the summit of Mauna Kea. And the Sphere instrument, which is in the southern hemisphere, it's there on VLT. And all of these instruments, they are used there. They have the cutting edge technology to take direct images of exoplanets from the ground. We have other instruments like CAPIC at Keck Telescope. We have MAGEO at Magellan that I'm not going to refer, but I'm going to talk only about these three instruments. All right. Probably you have seen this many number of times. So there you have the number of exoplanets that have been discovered, and on the x-axis you have semi-major axis. On the y-axis you have the mass of these planets. And I'm not going to focus on the indirect detection techniques. I'm going to only focus on these green dots here, which are the directly imaged planets. And you immediately notice here that the planets that have been directly imaged, they are giant planets and lying very far away from their star. And they are the planets which are self-luminous. So I'm going to focus, my talk is all about if we know these planets exist at smaller angular separation, why we haven't been able to take direct images of these. So direct imaging from the ground has been really successful. So I'm going to present just some of the results. or some of the directly imaged planets from the ground. So on this slide, these were the detections made in early 2000 with first generation high contrast imaging instruments, for example, NERC-2 at Keck, NIRI and Niki at Gemini, and NACO at VLT. That were the very first images of exoplanets that we were able to get from the ground. Then with a little bit of improvement in the technology, as well as the improvement in post-processing techniques, we were able to get more images of planets at smaller angular separation. So this is the discovery image of 51 Eridani b by Gemini Planet Imager instrument, and this one is the detection with the SPHERE instrument. And here you see a protoplanet, a directly imaged protoplanet using SKEX-AO instrument. It was very recent, actually, just about roughly 2 years ago. Direct imaging is pretty cool. You can even see planets in orbit, and we've been able to see that on the ground as well. We have also successfully imaged debris disk, and we are, from the ground, are able to resolve spatially some of the disk features as well, like shadows, cavities, spiral arms, and whatnot. And we can also characterize them both in spectroscopy and polarimetry as well. Now, let's talk about what is the technical challenge that we face in high contrast imaging. So before I explain you that, on the left side of the plot, let's look at what are the contrast requirements in general. So here on the left side, on the x-axis, I have wavelength, and on the y-axis, I have the the contrast of the solar system scale planets. And you immediately notice that in order for you to find an Earth-like planet in reflected light, you're talking about the contrast of 1 billion times that you need to get in your image. For the Jupiter, it's kind of like billion time contrast that you need to get. And if you kind of move towards a longer wavelength, the same Earth-like planet would be at a relaxed contrast. So at 10 micron, the same planet would be at a contrast of 10 million times. And also, like if you look at the young Jupiter, so young planets, the contrast is even more relaxed. So to image a young Jupiter, the planet in infrared is mostly a million times, and that's where the ground-based high contrast imaging instruments are more sensitive to finding young planets. And on the right side here, you see the contrast versus the angular separation, and then you immediately notice the contrast curve of the state-of-the-art instruments, so Gemini, EPI at Gemini, and SPHERE at VLT. You immediately notice that the contrast level that these instruments are able to produce is of the order of million, starting from like beyond 100 or 120 milliarc second. And so the reason we've been able to image like hot Jupiter, young planets, young Jupiter-like planets, is because of the contrast that we can achieve with the current state-of-the-art technology from ground. And these red dots are the directly imaged planet in the infrared. And the one in gray are the planets that have been discovered by RV, but this is the predicted reflected contrast. So with the current instrument from the ground, we cannot image those planets, which are already using the RV. So the idea of the next decade, the idea of these instruments is to be able to improve the contrast by at least a factor of from 10 to 100, so that we can image mature planets at less than 10 AU. So right now, in present time, we can image planets which are massive planets but lying beyond 10 AU. So the goal of this talk is to basically help you understand why the current instruments cannot go beyond, why we can't get more contrast. So So I'm going to be, in the next couple of slides, kind of make you go through steps of how high contrast imaging is done from ground. So just to kind of remind you how an image is formed in a telescope. So if you have a circular pupil, for your transform of that, you get the PSF. You add some complexities in your pupil. If you add like a secondary support structure and also these spider arms, you kind of see that the light is diffracted around those edges as well. So this is kind of like is the diffraction limited point spread function. So when you observe a star-planet system through ground, your light is actually going through the Earth atmosphere. So there are some inhomogeneities that are introduced, inhomogeneities in the refractive index of air that introduce optical aberration that blurs out your image to the size of 1 arcsecond. Instead of getting like a diffraction limited image, what you get is a seeing limited image. And so you need adaptive optic system to be able to basically correct for those aberrations. So with the AO systems, you basically try to go from seeing limited image to a diffraction limited image. When we talk about classical AO system, we don't need to really have perfect diffraction limited image if it's non-exoplanet science. So we kind of talk about Strel ratio. So Strel ratio is basically defined as your aberrated peak intensity divided by your diffraction limited image. The closer the value is to 1, the better is your, the closer you are to the diffraction limited image. So with the classical AO system, if we are getting like a ratio of like less than 80% in image band, good enough for non-exoplanet science. But when we talk about exoplanet science, that we want to be able to actually get more than 95% of the ratio. So here is just a video, on-sky video from SCEX AO instrument where you see when you don't have an AO correction, that's how your image looks like. With the SCEX AO instrument, basically you have, the instrument is actually at the NASMIT platform, and SCEX AO instrument feeds on a classical Subaru AO system. So you start from seeing limited image, then you close the loop with your classical AO system. So in this case, it's AO188 at Subaru, AO188 system. You close the loop, you get to a diffraction limited image. So in this example, it's like Strel ratio, the PSF looks good, but it's not like the Strel ratio is not as high as you want for the high contrast imaging. So what we end up doing, we apply additional high order and low order corrections, and we do something called extreme AO. So in extreme AO, you want to have Strel ratio as close to 100% as possible. So then you go from AO correction to extreme AO correction. It may not be visible that much, but in the extreme AO correction, you see the light is more concentrated at the core of the PSF. So not all extreme AO instruments needs to feed on a classical AO system. So for example, GPI and SEER instruments, they are extreme AO instrument itself. So they go from seeing limited image correcting to getting the diffraction limited image. So extreme AO instruments have, there are some parameters that we need to take into account when we design an extreme AO instrument. So something is called coherence length, or like free parameter, called R0 in short. So this is basically, the R0 is basically, is the area over your pupil where the standard deviation of the atmospheric wavefront error is around 1 radian. The R0 value is basically also defines like it's the area over the pupil where the phase of the incident wavefront is coherent. So, and the value of R0 depends from site to site. So it's different on Mauna Kea, and it's a different value in Chile. And it also changes from night to night. So R0, a typical R0 value at visible wavelength is roughly 10 to 15 centimeter on the summit of Mauna Kea. So what it means is that any telescope diameter which is less than 10 centimeter would give you a diffraction limited image. But any telescope bigger than 10 centimeter will give you a seeing limited image. So it doesn't matter if you have a 10 meter class telescope on Mauna Kea, you're not going to get a diffraction limited image if you don't have an AO system. because your R naught is roughly 10 to 15 centimeter under very good seeing conditions. And R naught value is also what helps you define how many actuators you need to be able to get good extreme AO correction. And another factor is called coherence time, so tau naught. Coherence time is basically it's how it tells you how fast you need to run your AO system to catch up with the turbulence. So it's so it depends on the wind speed as well as the coherence length. And so it's roughly 5 milliseconds for an R naught of 10 to 15 centimeter. And tau naught is something that basically tells you how fast you need to run your AO systems. It defines the closed loop bandwidth. So you want to be able to basically sample your turbulence 10 times more than the required closed loop bandwidth. And I'll tell you why I'm talking too much about this. These numbers will matter later on to kind of help you understand why extreme AO is so difficult and why we can't actually correct all the aberrations and then get the contrast that we need to find more planets. So just to kind of help you understand more visually, what does it all mean? So there's always a delay between when you sense an aberration and then when you correct it. And you want that delay to be as small as possible. And you have this delay because you're taking time to measure the aberrations, and the readout time as well, then you compute the correction, then you send the command to the DM, and then there's a bunch of like hardware, software delays. So if, let's say, you measure some aberration at time t at 0 milliseconds, and you apply the correction after 1 millisecond, your turbulence has already moved. So if you take the difference between the two, you see some residual turbulence. Since you didn't correct it, it will manifest as a residual aberration in your image. So another way to look at the same thing is that, let's say you have like a phase, you measure some phase, the wind is like 10 meters per second, and the delay in your measurement and your correction is 2 milliseconds. And you measure this phase, and then you apply the correction, and then you have like low residual because the wind speed is not that bad. But when you increase the wind speed, you kind of see that you have more residual in your image because the wind speed is basically making coherence time go even smaller. So your AO or extreme AO cannot catch up with the turbulence. So you kind of see this light scattered in your image, and this scattered light is kind of like in the direction of the wind. And this is something called wind-driven halo that all of, yes? Oh, so can you? So it depends on R naught value as well, and so it keeps on changing. But at a typical site, for example, in Chile, it's like 2 milliseconds roughly, and then on Mauna Kea, because you have a little bit better seeing, so it's kind of like 5 milliseconds. Oh, I see. Okay, it's more relaxed. So the longer in wavelength you go, your R naught value becomes more bigger. Yes, and so wavefront correction is a little bit better at longer wavelength, but then you lose the angular resolution because your diffraction limit gets larger, so you don't really have access to small angles. You want to find planets at small angles because your angular resolution is not as good as in the visible. So anyway, so this is called something called wind-driven halo, which is a big problem both in Chile and in Hawaii, and that happens because you have like at like high altitude, like 12 kilometers roughly, you have jet stream passing by, and they create wind speed of like 50 meters per second, and that scatters your PSF in a radial direction. And we're not fully able to correct this with the present state-of-the-art technology. Anyway, so let's assume that you have like your AO is working well, your extreme AO is also giving you the diffraction limited PSF. What you do, you then put a coronagraph at the focal plane of the telescope to block the light of the central on-axis star. And it's important to have the cell ratio as close to 95% as possible because you want all the starlight to be concentrated at the core of the PSF so that you can block it with the coronagraph. So pretty sure I don't need to show you this, but it's just kind of like I have a simulating a vortex coronagraph, and I'm just moving the PSF across just to kind of show you, like, if you have a planet, you can see a planet when you add a coronagraph in your. But if you have like a very complicated pupil, for example, this is a TMT pupil. So TMT is 30-meter telescope. You're going to see even after the coronagraph, you have some residual diffraction, and you can subtract it out in your post-processing, or you can also apotize your pupil to kind of smooth out the effect of the diffraction around the spider arms. Anyway, so there are a bunch of problems that we go through in extreme AO from ground. So one is low order aberration. So it happens because of the thermal distortion, pointing errors, and the chromaticity of the atmosphere as well. So here's an example of on-sky example from Subaru, where you have good enough AO and extreme AO correction, and this is your PSF, and that's your vortex coronagraph, and then you see that it's not, the starlight is not aligned behind a coronagraph because you have low order aberrations. So you need to have a dedicated low order wavefront sensor to make sure that your star is perfectly aligned behind the coronagraph. And this particular low order wavefront sensor is what GPI2 will have. You also notice in this image that even though you have like good AO, extreme AO correction, and your starlight is also suppressed, your low order wavefront sensor is also working fine, but you see a lot of speckle noise. And this is basically these are the fast-moving speckles because of these are the atmospheric speckles that moving really fast, and your AO cannot correct it. So what happens, like when you have a raw image, when you look at a raw image coming out of an extreme AO system, this is the lab image, and this is the on-sky image. So you see a bunch of things here. First of all, what you see here in the lab image, let's talk about the lab image first. This ring is called the AO ring. So this is the AO correction. It depends on the size of this correction, depends on the number of actuators you have. Then you kind of see it's a faint halo here, but you see a residual halo. So this is, if you take a long exposure, then all the atmospheric speckles, they kind of average out, and they add photo noise to your detection. You kind of also see static speckles, and they kind of like, they fairly stay stable, and you can subtract them out in post-processing. See another feature, which is called quasi-static speckles, and they are a real problem from the ground, because quasi-static speckles, they are introduced in your system because of the non-common path aberrations. So you're basically, in extreme AO, your sensing and your imaging channels are different. When your sensing and imaging wavelengths are different, they add quasi-static speckles. Sorry, they add non-common path aberrations. So if your non-common path aberration is evolving while you're acquiring your images, the quasi-static speckles are going to evolve as well. So in your sequence, you would have some quasi-static speckles that kind of like may look like a planet, but they may not be a planet. So it's really important to suppress them in real time while your AO loop is closed, and that's extremely difficult. And in the on-sky image, you see kind of like more additional problems. So again, this is the wind-driven halo that I was talking about, and that kind of like completely overwhelms the AO-corrected region. So you can actually use focal plane wavefront sensing to deal with the non-common path aberrations, and what we basically do in extreme AO. So one such technique is called self-coherent camera, and I can talk about it more in details if you want to know how this works. The idea is, again, you use your science image itself to measure the speckle field, so the amplitude, the intensity and the phase of the speckle field, and you suppress them in real time. So this is just a lab example where you start with your image with a bunch of static and quasi-static speckles, and then you use a DM to create a dark hole, full dark hole, and a half dark hole. And you create a half dark hole, then you're suppressing both amplitude and the phase of the aberrations. And in this particular example, you kind of see a lot of leakages around the central star because the lower loop wasn't closed. So the idea is basically that once you do the extreme AO correction, you get a very nice PSF. You suppress your PSF with the on-axis PSF with the coronagraph, and then you want to be able to suppress those quasi-static speckles on sky in real time. And that we have not been able to, we have tested several techniques. For example, the slide kind of shows the EFC, the electric field conjugation. So we have tested on sky, closed the loop with EFC on SEER instrument at VLT, and they were able to get the contrast of like 1 million, 10 to the power 6 at 5 and beyond, 5 lambda on D and beyond. And with the MAG-AOX in lab, similar kind of algorithm was able to get much more deeper contrast. So everything works well in lab, but not on sky. So when you take, like, I mean, this, even though like the SEER instrument, they were able to create this dark hole on sky, but the dark hole was not stable. So it worked for a while and then everything broke. So the idea basically is to be able to have these focal plane wavefront sensing running on sky and create a stable and dark hole throughout your observing sequence. And that's the goal of GPI, upgrade of GPI as well. So GPI 2 will have this technique, self-coherent camera, to dig the dark hole, and I think they're going to also implement EFC as well. Okay, so correcting, so I think I'm just going to repeat myself, like we need to really correct quasi-static speckles on sky, and that's the problem, one of the problems. And again, that is again the reason why we can't actually get a deeper contrast at angles, because we have a lot of scattered starlight. Okay, so once you have, you suppress the starlight, then you kind of rely on post-processing techniques, and there are a bunch of them out there. And some of them are called angular differential imaging, reference differential imaging, polarimetric differential imaging. I don't think I need to go in too much details here, but the idea is that whatever your extreme AO could not correct, you correct it in post-processing. And once you have your, everything, suppressed, your static and quasi-static speckles are suppressed, and you kind of send it to an IFS if you have an IFS in your instrument. So IFS, the integral field spectrograph. And this is just an example of a raw IFS image from GPI, and you can kind of see the beta pic signal here as well. So in GPI, the IFS is basically in the IFS instrument at the focal plane, you have a grid of lens slit. The light passes through the lens slit, and then it goes through the dispersive element, and then you kind of see a bunch of microspectra in your IFS, and then you can take that microspectra and then convert it into a multi-wavelength tube to get the spectral information out of the planet. So here I'm kind of like summarizing all of the, like whatever I talked about so far, like all of the problems that we face from the ground-based high contrast imaging instruments. So there are a bunch of static defects that we can correct out in post-processing, but there are dynamic errors as well, and we're not fully able to suppress these errors at the desired angles, especially at the small angles. So that's basically, again, to remind you, the instrument, the current state-of-the-art instrument are limited at the level of contrast that they can achieve at present with the current technology. So now let's briefly look at Gemini Planet Imager 1. I'm sorry, it's going to be a little bit technical, but I'm going to just skim through the technical aspects of it. So as I said earlier, GPI 1 was operational for 6 years in Chile, and it operated from 2014 to 2020. And so the GPI instrument has 2 deformable mirrors, so one in a woofer system and a Twitter system. And it looks at the raw, the scene limited image, and it does not rely on any classical AO system. It corrects the PSF and try to get the as high style ratio as possible. So GPI 1 had a Shack-Hartman wavefront sensor to correct for to measure the wavefront aberrations, and it could run at 1 kilohertz on fairly bright targets. If you were observing targets fainter than 8 mag, the IMAG of 8, then loop would struggle a little bit, and you would run slower, like the loop speed would go down. And the moment the loop speed is going down, imagine you're not correcting as much as you want to correct, and your contrast also degrades. And GPI 1 has APLC coronagraph with the, I think the focal plane mass diameter, or the radius is 2.8 lambda on B. And it has an excellent data reduction pipeline. So when you're observing, when you're doing the observing sequence, like within the same night, you can actually get the differential imaging reduced, ADI reduced images not long after the observations are done. So these are some of the results from GPI-1, and there are several talks out there that talk about all of these, the planets and the brown dwarfs that GPI-1 has discovered, and they have characterized the atmospheres of all of these planets as well. I'm not going to go too much in detail. This is the GPI also did a survey called GPI's survey. So this is the depth of search plot. On the x-axis, you see a semi-major axis, and on the y-axis, you see the mass of the planets discovered. And so in the GPI survey, they kind of looked at roughly 300 stars, and they detected 3 brown dwarfs and 6. And the idea of this survey was to kind of understand the planetary demographics and to also see, understand how many planets they can find that favor hot star planetary formation scenario versus the cold star, and how sensitive the GPI instrument was to finding these different population of planets. And from what I understand, I think GPI-1 was more sensitive to finding hot star planet because it could not achieve the contrast that it needed to find the cold star planets. And they also, in their survey, they also concluded that the wide separation giant planets, they are more common around high mass star than the solar type stars. And they also figured that the most Jupiter type planets, they lie more at less than 10 AU. So this was what GPI achieved scientifically, but they were also able to use the telemetry of GPI instrument to kind of understand the technological limits of the high contrast imaging instruments. So on the left side, it's a plot by Olivier Guillaume, where you see the contrast versus the wavefront sensor guide star. So in your extreme AO, your science star is your wavefront sensor guide star as well. So the moment you go to the fainter limit, you kind of like are limited by the background noise, and your AO loop cannot cope up, and your contrast degrades as well. And this is something GPI-1 was also able to kind of confirm. So on the right side, what you see is basically the 5 sigma contrast of 25,000 coronographic IFS images, and as a function of 3 different angular separations, contrast at 3 different separations. So the gray one is at 0.25 arcsecond, so small separation. The red one is at 0.4 arcsecond, and the cyan one is at 0.8 arcsecond, as a function of the wavefront sensor guide star magnitude. So you immediately see that this is at the top, these are the bright targets, and at the bottom, these are the faint targets for GPI-1. So as you go towards as you go fainter, your contrast degrades. That's what this graph is showing. So the contrast at small angle is not as affected by the limit of your guide star, because at small angle, you're mostly dominated by the coronographic leaks because of the low order aberrations. If you go to 0.4 arcsecond, then you're mostly limited by the atmospheric speckles and quasi-spheric speckles. If you go a little bit further, that's where you are more background limited, the fainter you go. So that's what GPI was also able to kind of confirm using their telemetry, some of the technical lessons that we learned from this instrument. Another interesting thing was that what GPI-1 concluded that the biggest culprit for contrast degradation was the tau naught value, the coherence time that I was talking about before. So at Gemini South, the tau naught value was 2 milliseconds, so the turbulence was was changing way too faster than what GPI AO could correct, so their contrast was limited. Just like if you just take the GPI instrument with its current technology and you just move it from Chile to Hawaii, the contrast would improve a little bit already just because the tau naught value is a little bit better. And something else that they also were able to figure is that contrast is also a function of the dome scene. So if inside your dome, if the temperature of the primary mirror, if it's like the temperature difference between the primary mirror and the ambient temperature, if it's more than 3 degrees Celsius, then contrast would degrade as well. So we were able to actually understand and learn all of these lessons from this instrument. Well, so now we are doing a grade of this instrument because we want to be able to improve the contrast and get more, find more planets at small angles. So GPI2, so the idea of this upgrade is to basically, on the left side, so on the left side, this is the simulation, Monte Carlo simulation of the universe, also including the lessons learned from GPI1. In gray, you kind of see the contrast, most of the contrast level that GPI1 was able to get, and black curve is the contrast curve that they're hoping to get with GPI2. So if GPI2 on Mauna Kea can get this contrast level, so get the factor of 10 to 100 improvement in the contrast at small angles, then they would be able to find more planets which favor like the cold start planet basically. So this is also on the right side, the science cases. So we want to be able to basically get good performance for the faint targets and improve the contrast as well at small angles. And GPI2 will also be, yes?
Is there a difference between the filled circles and the open circles?
Yes, good question.
Could you repeat that question?
Oh yeah, so the question is what's the difference between the filled circle and the not filled circles? So from what I understand, when they did this simulation, I think the red one is the hot star planet and the blue one is the cold star planet. This is what they, during this simulation, this is what GPI1 should have detected, but the filled one. But these are not the planets that GPI1 detected, and detected 4 other hot star planets, if I'm not mistaken, but not the one which is mentioned in this simulation. And I think it's because the contrast really is a function of the seeing conditions. So if your seeing is bad, then maybe there's a planet over there, but you can't really see it because of so many problems that I've discussed already. Okay, so GPI2 would also be able to do non-exoplanet and non-chronographic science as well. I'm not going to go too much in details, but you don't need a high contrast level for those science. You just need to be able to close the loop on fainter targets. So the current limit, the IMAG limit is roughly 9. So any star which is fainter than that, GPI2 AO loop kind of struggles. So with GPI2, we would be able to basically go to IMAG limit of between 10 to 14. So here are some of the upgrades. So on the left side, this is what GPI1 had, and on the right side, in green, it's what GPI2 will have. So the main differences between the two is first the AO wavefront sensor. So we are going from Shack-Hartman to pyramid wavefront sensor, and pyramid wavefront sensor is more sensitive for correcting aberrations around faint targets, on faint stars. GPI2 will also have a new real-time computer as well, RTC, which is called HART-RTC, being developed in Canada at HAA. And it's going to also have a low-resolution mode in the IFS. It's going to also have, GPI2 will have the same APLC, so the focal plane mask diameter is not going to change, but they have already optimized the apodizers and the Leostar to basically improve the contrast at small inner working angle. And GPI1 had something called Cal unit. Cal unit was there it has a dual arm interferometer. It was a dual arm interferometer. I'll show it to you later on, which was built by JPL, but it never worked on sky because of vibrations.
What's their? Why didn't they?
I think it's yes. So the question is, what's new? Why didn't they do it before? Like, why didn't they upgrade? Sorry, why didn't they? What's new about the pupil plane mask? So this is basically the technology. You know, the GPI-1 technology was locked like 15 years ago. So I think it's with time we learned from the. I think I kind of talk about later on. Like, we learned from the APLC design has also improved with time. So been learning from what they have been done for the space-based telescope. So been learning lessons from all the things that have been done for space study. So that's why, like, it wasn't there during GPI-1, but it will be there during the GPI-2. But I don't know exactly what's been changed, but it's more optimized depending on the angle and the angle at which you want the high contrast. So I think it's a design done by Mamadou, if I'm not mistaken. So both the apodizers as well as the new LEO star. That's all I know. Okay, so the pyramid basin sensor is designed again at HAA in Canada, but it's built in San Diego, and it just shipped a week ago to the Notre Dame University. That's where the GPI-1 instrument is, and that's where everything is going to be. Everything's going to come together. So the pyramid basin sensor is on the way, and when it's there, then I'm going to go and then test it with the team. Go through the acceptance test and planning and see that pyramid basin sensor is doing what it's supposed to do. So this is some of the simulations of what pyramid basin sensor would be able to do. So on the left side, well, in both plots, you have star magnitude on the x-axis, and then you have star ratio on the y-axis. And on the left side, it's the performance of the pyramid basin sensor at different loop speeds. And on the right side, it's different scene condition, and you kind of just see that a star ratio is going to degrade nicely when you're going to go more fainter than 14. It's not going to be great, but it's going to do better than what GPI-1 did. So again, the better is your AO correction, the nicer is your PSF, and less aberrations you have at small angles. This is, I don't know exactly what's been changed in the LEO stuff for the new apodizers and LEO stuff for GPI-2, but it's been, the design are basically based on what's being done for the space for the APLC. So this is what I was talking about Cal2. Cal2 is something which is going to help get a deeper contrast with what GPI-2 would already be. GPI-2 will give you some nice contrast, but Cal2 will make it even more darker. So just kind of explain you a little bit, like GPI-1 had this Cal unit, which was a dual arm interferometer, which did not work because of vibration. But what's going to happen in Cal2, again, Cal2 is being developed in Victoria, and the PI is Christian Marwa. So in Cal2, basically, you will have a LEO star, which will, it's a common path interferometer, and you will be able to basically, it will be more robust to vibration, and it will have something called SCC, which I was talking about earlier, self-scoring camera, to suppress the quasi-static speckles in real time. This is kind of to show you roughly how it's going to work. This is the rough optical layout of a chronographic system. So if you look at the LEO plane here, so in a classical LEO, in a classical system, your LEO stop is basically, it blocks the residual starlight. But in case of Cal2, this LEO stop is reflective. So whatever light is being blocked by the, well, it's not being blocked by the chronograph, it's just being sent to a different direction in your LEO plane. So LEO plane basically has a reference hole as well, and it's reflective in nature. So instead of simply blocking the residual starlight in the LEO plane, it's going to send it towards a different channel to do low elevation sensing, and then it's going to send basically some of the starlight is steered towards this reference pupil. So the starlight will go through this reference pupil, but then if you have aberration in your system, which you always have, it's going to go through the main pupil, and then in your final science focal plane, you will see fringes because you assume that your star is a point source, and whatever is coherent will all be fringed, but not your planet. Then you can actually use those fringes to measure the speckle field, and then apply the correction on the DM. Yes, so that's what I was showing earlier when I was showing the video of closing the loop. That was done with SEC. That was just quickly to explain what GPI-2 will have, but there will be some challenges at Gemini North, and one problem is going to be vibrations. So this is the Gemini telescope, and all the instruments, it's a Ritchie-Chrétien design, and all the instruments basically are at the Cassegrain focus. This is called instrument support structure, and all the instruments kind of like sit around this instrument support structure. You can have like 4 instruments on the side and then 1 at the bottom port. And all of these instruments, it's a pretty well-known problem both at Gemini South and Gemini North, that these instruments, different instrument that this telescope has, they have like they have cold heads, and you can imagine like all of these instruments operating at installed at the same time at the telescope have their cold heads running, injecting vibration, not only giving vibration to the other instruments, but also sending vibration to the telescope itself. And so Gemini Observatory is a very efficient observatory in the sense that it doesn't waste any time. It has a queue scheduling, so you already know what kind of the observations that you're going to do, which instrument you're going to use, and it's pretty easy to switch the instrument at night as well. So let's say if you have, so at GPI had a problem with vibration, so the main source of vibration was its own cold head itself. So this is the first light, this is the first light, this is the first light image of GPI, and you kind of see this focus kind of aberration, and this is the cold head of the GPI instrument itself. And so this was what they saw when they were testing, when they tested GPI-1 on sky. There was a vibration that was injected at 60 hertz, and GPI was able to basically suppress. They installed the active. Blacking out. Sorry. GPI-1 basically implemented something called LQG in their controller, filter, and it notched down some of the frequencies. And they also improved. They didn't get rid of this cryocooler, but they were able to basically actively damp the vibration as well. But what the 60 hertz vibration did to the telescope is very interesting. So Gemini, at Gemini South and also at North, there's a vibration team which is kind of doing shaker tests. So they are kind of like taking the whole structure to kind of recreate what GPI cryocooler injected into the telescope structure as well. So what you see here is some of the sensors, the accelerometers that were installed. The red one were installed, I think, on the mirror itself, and the blue one were on the mirror cell. And they were able to kind of like recreate what GPI-1 injected. So it's kind of like a focus kind of an aberration. So your whole mirror was actually moving in focus, which obviously impacted the GPI-1 image in return. For GPI-1, there was also a problem with the M2. There was some bad fence at where the M2 mirror was, so it's also injected vibration at 37 hertz, which GPI-1 was able to notch down with their LQG controller. This vibration problem will be there for GPI-2 as well, and we don't really quite understand how that's going to be translated with respect to the other instruments. So Gemini is going to have something called GNAO, so their new captive optic system. So how other instruments will be affected, we don't know yet. So the idea is that either you turn off the cold head of GPI to basically not getting impacted by what these vibrations are doing, or you not have other instruments on the ISS and just have GPI, and that will not be efficient for the Q observing. So it's a project that's going on in progress, and we've been talking between different instrument builders to kind of see what kind of vibrations they will be bringing in and how it will affect their own, how it will translate to different instrument and to the telescope structure as well. Another big problem, which is a very known problem, this is my second last slide. The big problem, which is a well-known problem at Gemini North, not at Gemini South, but at Gemini North, is the M2 print through. So this is just the M2 support structure, which kind of like have like this print through that's going to be more visible for GPI2 images under very good conditions. And you can, I think Bruce McIntosh has done this simulation where you kind of see that the contrast will degrade as well because of this M2 print through, which is going to spread the light within your dark hole, but probably you can suppress it in post-processing. So in short, to summarize quickly, so with the current state-of-the-art high contrast imaging instruments, we are able to basically find Jovian-like, giant Jovian-like exoplanets lying far away from their star, just because of the limitation of the contrast that we have. We can't dig a deeper contrast at small angles because of all of the problems that I've discussed. And the idea is that the upgrade, so GPI2 upgrade, and XAO is doing its upgrade, Sphere also going to do its upgrade, and it's going to be called Sphere Plus. And the idea is to basically suppress the speckles at small angles so that you get the contrast improvement of at least a factor of 10 at small angles, and you can basically reach lower mass planet at closer separations. And to briefly talk about ELTs, so we are in the era of extremely large telescopes. So we have 30-meter telescope, we have European ELT, we have GMT, and these are like GMTs, like 25-meter diameter telescope. So again, if we can with GPI2 and Sphere Plus, if we can actually improve the contrast by a factor of 10, that's going to give us, it's going to increase the science even a little bit at small angles from the ground. But we'll have to wait for ELTs to come if we want to find Earth-like planet, because ELT will be more sensitive to finding Earth-like planet around M stars because the contrast is a little bit relaxed, and it will also it will be able to image planets closer in thermal emission around FGK stars. But then taking these upgrades and putting it on ELT is not going to do the job. We would have to actually continue making the improvements with with the current technology. For example, we need to be able to run faster than what tau naught allows. We need to have a high number of actuators as well. Like right now we have like 2K DM. We need to have as many actuators as possible to be able to correct for the high frequency errors. We need to understand how we can also calibrate the PSF using the telemetry, the system level telemetry. So getting the telemetry from the wavefront sensor, from the deformable mirror, from the temperature sensors, humidity sensor, and accelerometers, and then basically be able to calibrate the PSF better. I think I'm a little bit over time, but I'll stop here and I'll take any questions you have.
We have one question from online. Mike, are you still online there? Mike McQueen.
Yeah, yeah, I am. This was a great talk. Thanks so much. I guess I had two questions I put in the chat. So I think you made a compelling argument that the best atmospheric conditions, the best tau naughts, are really impactful to the quality of the science data. So is the Gemini Q being used to prioritize those best nights for these observations, or at least some subset of the observations?
So wait, I don't think I get the last. Can you please
So
repeat the question?
yeah, yeah, sorry, I don't know how well you can hear me. Maybe someone else could ask the question if need be. But you made the case that the best atmospheric conditions really improve the contrast that's achieved. There was a plot.
I see your question now. Yeah, I think I understand your question.
Yeah.
Yes. So at Gemini, basically, you have like 4 bands programs. So band 1 is the highest priority program. Band 2 is the little bit lower priority. Band 4 is like when you have like a lot of cloud condition. So Gemini is used to having like prioritized observation. So for the best atmospheric conditions, all the band 1 programs are executed. So Gemini is very efficient in doing that, and it will do the same thing with GPI2 as well.
Yeah, I guess a follow-up. Yeah, so I was familiar with the bands, but is band 1 fine enough of a scale, or is it still too coarse to capture the tau naught that you really want for your observations? Or is that sufficient?
So we can't really do much about tau naught. We just get what we get. So I think whatever we're gonna get, that's what's gonna well, to basically go faster than tau naught, we really want to be able to measure aberrations at 2 kilohertz speed, or even more than that. So if GPI2 can do that, then yes, we'll be able to basically get the best observation at whatever tau naught is we're gonna get per night. But we will be limited again by how fast we could run, and that's defined by the wavefront sensor. I forgot about mentioning the EMCCD that they're going to have. So it will be limited by how fast we can actually correct anyway. Or will be limited by how fast we can go.
Okay.
Does that answer your question?
Yeah, I thought it was a combination of how fast you can go and the tau naught at the time of the observation. But I think I understand the response. And then the other question, you had shown that there was a 60 hertz cyclic frequency, and I was just curious if you had the ability to tune your cryocooler. You might have mentioned that, I didn't hear. But you were doing a modal survey of the structural response, and you could potentially change the pulse frequency to, reduce the coupling into the structure.
I don't have an answer to that, and I'm pretty sure GPI2 is looking into that. I think we will be having this conversation. We're already having this conversation actually with the internal Vibration Gemini team and the GPI2 team. So I don't know exactly what's going to be done, but GPI2 will have 3 cryocoolers actually. Alto will bring its own as well. So I don't know exactly what's the plan as of now.
Okay. Thanks so much. Great talk.
Thank you.
That was a super nice talk. Thank you so much. Very, very good explanations. On the last slide, you were looking at thermal emission from Earth-like planets or terrestrial planets. In what sense will the atmosphere be a challenge there?
So you do get like high background emissions. So at present, like if I'm not mistaken, with the current facility, you obviously have like relaxed contrast at longer wavelengths. So I think with the current facility, we can only look at alpha SN A and alpha SN system. If we have, we'll have to have a higher exposure time, okay, but we'll be limited by background emissions. Right. So that's what's possible. So we'll have to wait for ELT.
Yeah.
I think it's just like beyond 3 micron. It's just.
Yep. Yeah, that was kind of what I was.
Yeah. So we'll have to like wait for ELT, yeah, to be able to basically do that.
But they would have the same challenge, correct?
We'll have the same challenge with ELT as well, but we will have yes, we will have the same challenge, but I think you can optimize your exposure time a little bit better, okay, with the ELT, so that would help.
Okay.
Larger, yeah.
Sure. Okay. Yeah, thank you.
Around, yes, yeah. That's what like we were waiting for with ELT.
I'll talk to you later.
Okay, sure.
Online also, I don't see. Let's thank Garima now. We are going for lunch.